So, good evening. I'm Calvin Joseph, and today I'll conduct your week 4 problem solving and doubt clearing session for the NPTEL course Digital Circuits. Okay, so this is basically the course content, the lots of stuff which you'll be studying. So, this week we'll be focusing on logic gates and some few bit of arithmetic circuits also Suresh touched upon. All right, and then so this is what we'll try to look into today. What are logic gates? What is SOP representation in terms of NAND gates? Why NAND gates, NOR gates are universal gates? Okay, what are XOR and XNOR gates? And these are certain things which were touched upon. Okay, let's see how much we can do. So, this week 4 and we are doing what is SOP and POS based representation. That we have studied a lot of times. So one thing is in a SOP based representation, what it is sum of products. Sum of products, right? That is, let us say you have this circuit, right? This is A, B, A bar, B bar, something like this. And then it is odd. Okay. So this is the summing operation. This is the product operation. Okay. This is your SOP based representation. What sir has shown is you could make not this as well as not this. Not this as well as not this. Will it change your output? Will the output change? That is, you not it over here and then you again not it over here. So you'll get back the original signal. You will again not it over here and you will not it over here as well. So you get back the same original signal. So your actual output, that is your output Y, will not change. Okay. Then what is your new circuit? Your new circuit in that case will become, it will just consist of NAND gates. It doesn't need anything else. It will just consist of NAND gates. Okay, you have A here, B here, A bar here, B bar here. This is your output Y. Okay, so this, so what do we are doing is we are representing the logic gates, which are an SOP representation using NAND gates alone. And for the in the course also when sir was teaching regarding CMOS based representation, he would have showed you about how NAND gates look when you have a CMOS based circuit. Okay, and NAND gate will require only 4 transistors. So that is an advantage of a NAND gate. Okay, that's why it is preferred and other stuff. Okay, so now this is circuit is Y. Okay, this circuit Y. What is the Boolean expression for output of Y? Can anyone tell? What is the Boolean expression for the output Y? You can either type it or you can either write it.
AB bar dot AB
Now,
whole
if you
bar.
are telling what is Y, I mean to say Y is what? It is what A and B plus A bar and B bar, right? This is your Y. Any
Yeah.
doubts, please?
Yes, sir.
Yeah. It's not A XOR B, it is A XNOR B. So this is actually your A XOR B. XNOR B. Yeah. So basically this circuit is doing your A, B, XOR gate, and you have a NOT, so this is an XNOR gate. Okay, this is an XNOR gate, right? Now, this XOR, XNOR gates are very useful. Let us dive into it. So you have XOR, XNOR. Okay. Truth table is 0, 0, 0, 1, 1, 0, 1, 1. So what is the XOR output? Can anyone tell?
0110.
Hmm?
0110.
Okay, so XOR output is 0, 1, 1, 0. XNOR output is what? 1, 0, 0, 1. So now, if you know the min term is what? This is M0 min term. That is equal to A bar and B bar. M1 midterm is what? A bar and B. M2 min term is A and B bar. And M3 min term is A and B. Right? This is how it is. So if you see your XOR gate is summation of what? M1 and 2. And your XNOR gate is what? It is the summation of M0 and 3. This is how you represent your XOR gate and your XNOR gate. Okay. Now, when we will draw the K-map of this is very simple. XOR gate. This is, let us say, this is your A, this is your B. This is 0, 1, 2, 3. So here you have a 1, here you have a 1. For the XNOR gate, how it becomes? A, B, 0, 1, 2, 3. This is a 1, this is a 1. Okay, so this is your XOR gate. This is your XNOR gate. Now, you focus on this. So this is your A bar. This is your A. This is your B bar. This is your B. So your XOR gate will give you a 1. It will give you a 1 when there is only a single 1 in your circuit input which is high. XOR gate gives you an output high, that is 1. Let us say it will give this output 1. When does XOR gate give output 1? When any of the inputs, when an odd number of inputs is 1. Okay. So the XOR gate, that's why XOR is known as an odd function. XOR gate is an odd function. On the contrary, for XNOR gate, here what you're getting, output is 1, but your inputs, how many ones are there? There are 0 ones. Okay. Here your output again is 1, and in your input, how many ones are there? 2. So it is either 0, 2, and so on. That's why your XNOR gate is known as an even function. Your XNOR gate is known as an even function. Okay. And when you look at the K-map for XOR gate or XNOR gate, what you will observe is that you cannot do any, reduction or grouping. It's not possible, right? You're not allowed, to combine like this. That is not allowed. Okay. So these are certain characteristics of your XOR and XNOR gate. And because of this, people have found various uses of XOR and XNOR gate. It can XNOR gate, uh, XNOR. This is can be used for equality detection. It could be a part of that. XOR is kind of like when it is not equal, then it gives you an output high. XNOR is when the inputs are equal, it gives an output high. Okay. So there are various uses of XOR and XNOR gate. I like to ask a question. What is A XOR B bar? That actually is equal to A bar XOR B. This is one identity which you must know. Okay, let me start with a simple identity so that it becomes easier for you to understand. Suppose you have A XOR 0. What will the output be? What will the output be of A XOR 0?
A.
So A
A.
XOR 0 is 0, right? What is A XOR 1? Sorry, A XOR 0 is A. I'm so sorry. A XOR 0 is A. What is A XOR 1?
A.
Okay, A XOR 1 is actually equal to A bar. So let us see. You have, sorry, you remember the truth table, na? A, B, 0, 0, 0, 1, 1, 0, 1, 1. And this is your XOR output. XOR output is what? 0, 1, 1, 0. So now your B, for this case, for your B in this case, what is that? B is 0 and here it is 0. So in that case, when you see the output of XOR, when A is 0, output of XOR is 0. When A is 1, your output of XOR is 1. That's why A XOR 0 is A. Similarly, when you have the case of A XOR 1, so you have 1 over here, 1 over here. In that case, what is the output of your XOR gate? Here A is 0, your output of XOR is 1, right? Here A is 1, your output of your XOR is 0. So that's why A XOR 1 is equal to A bar. A XOR 1 is equal to A bar. Okay, so these are certain properties of your XOR gate, which are very useful. So another thing is, let us say, what is A XOR A? What is that output of that? A XOR A.
0.
0.
Oh, I cannot hear actually. I'm not able to hear. Is it? Can
0.
someone tell? I'm not able to hear. Hmm, just 1 minute. 1 minute.
0.
Okay. So A XOR A is actually 0. And A, yeah. Just give me a minute. Just give me a minute. I don't know why I'm not able to hear. So let me just check 1 minute. Okay, can anyone now unmute and tell so that if I can check if I can hear?
Okay. Can you hear?
Still, I'm not able to hear. Uh, check. Hmm. Tell.
Can you hear me?
Yes, I can hear. I can hear. Okay.
Okay.
I actually don't know why it was not able to hear. Mm, yeah, sorry for the inconvenience. So now, let's see. Yeah. So we understood that A XOR A is 0. What will be A XOR A bar?
1.
What will that be?
1.
Mm, Again, I'm not able to hear.
Why?
Mm,
1.
yeah, there's a still issue in the sound. Just reason. Okay, 1 minute. Let me just use my headphones. That will be better. Okay, can anyone unmute and say something?
Can you hear me?
Uh, can you can okay. Okay, so what is A XOR A bar?
1.
Yeah. A XOR A bar is 1. Okay. So these are certain identities which you guys would be familiar with. If you don't know, you can understand how these things are there, and it would be very useful for you. So let us check for a question where let us say let's say you have a function. Okay, that is A, B, C, D. You have 4 inputs. Okay, you have 4 inputs. And so let us draw the truth table. You have A, B, C, D. Your output Y is 1 when 3A, like whether A, B, C all are 1, 1 and D is 0. In the case, you have to have 3 inputs should be 1, then your output Y is 1. Okay, let us see. First we have 0, 0, 0. Then you have 0, 0, 0, 1. You have 0, 0, 1, 0, 0, 0, 1, 1. Then you have 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1. Then what do we have? We have 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1. Then we have 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 1, 1. Okay. So we want to find the output Y when there are 3 ones. When your circuit has 3 ones, then your output Y is 0. Is 1, sorry. So Y is here, what here? 0, 0, 0, 0, 0, 0, 0. But in here, in this case, your output will be 1. Why? Because you have 3 ones. You have 1, 1 here, 1, 1 here, 1, 1 here. So you'll have output 1. Okay. Let us see further. Here it is 0, here it is 0, here it is 0. Here it will be 1. Okay, here it will be 1. Similarly, further, let us check it is what? 0. Here it is 1, right? Here it is 1. Similarly, over here it is 1. And over here it is 0. Okay. So basically, we want to find a circuit where you have for odd number of high inputs, your output Y is 1. Okay, so for that, what we did was we first found the truth table. We found a truth table. Now, if you will look into the truth table, what is your min-term representation? Y is equal to summation of m. This is what? 7. This is what? 7. This is what? 8, 10, 11. This is 11. This is what? 13. And this is 14. Okay, so these are the min terms for such a function. So now let us try to generate that function. Okay. So to generate the function, what is the best way? We can use the K-map. So let's try generating the K-map. Let me write this over here. Y is summation of m 7, 11, 13, and 14. Okay. Let me rub this. Okay. Now we have to find y. So this is A, B, C, D. So what do you have? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, so what do we have in our case? We have for 7, 1. Then for 11, we have a thing. For 13, we have. And for 14, we have. So can you, what do you say, do any sort of reduction of this? Can you do any groupings for such a K-map?
No.
Yeah, you cannot do any groupings for such a K-map. Okay. So how will we write it further? So let us say this one. Okay, let me write first. This was 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. Okay, so this one over here, this corresponds to what? It corresponds to A bar B C D. Okay, then this one over here, what it corresponds to? Plus A B, and you have C bar D. Then this one, what does it corresponds to? It corresponds to A, B, C, D bar. Okay. And this one, what does it corresponds to? A, B bar, C, and D. Okay. Now, what do we do with this expression? How do we simplify it further? We do A bar B plus A, B bar, C, D plus A, B, C bar D plus C, D bar. How can we further write it? This becomes equal to A XOR B and CD plus AB C XOR D. Is it fine? Or any problem here?
No.
Okay. Yeah. So I want to ask a question. So is this function an odd function or an even function? Is this odd function or an even function?
Odd function.
Okay. So this is an odd function. Why? Because when there are 3 ones, then the output is 1. Okay, gotcha. Okay, let me explain it again. So, let me tell what is the question. The question is that you have 4 inputs, right? So you have A, B, C, D. Y will be high when 3 of the inputs are high. Okay. This is the function which we want to represent. It's a Boolean function we want to represent. So Y will be 1 when 3 of the inputs are high, any 3 of the inputs. Okay, so first what we found for this case, there is B is 1, C is 1, D is 1, Y is high. Then what we found the next case is over here. What is the case? when A is high, but B is low and C and D are high. Then the next case is what? When A, B are high, C is low and D is high. And the next case is what? When A, B, C are high and D is low. So we found out what are the 4 cases which we need. Okay, and I foolishly assumed that we can use the K map and we can do minimization, but I was wrong. Okay, in such a case, K map is not that useful. Okay, because we are not able to do any grouping or any combining the terms. It is not possible. Okay, so then I wrote Boolean expression of it, and then we combined the terms, and then we got it as A XOR B CD plus AB into C XOR D. Now, in this function, when you will notice this function, okay, you will notice, let us say, let us start with this term 1. How many bars are there? How many bars? There's one A bar, but B, C, D are all high, right? B, C, D is all not having a bar. So there are 3 ones, sort of. You can assume there are 3 ones. For the second term, how many bars are there? Is it 1 bar? Is there 2 bar? Is there 3 bar? How many bars are there? For the second term, you can see, right? There's only 1 bar, right? For the third term also, you can see there's only 1 bar. And the fourth term also, you can see there's only 1 bar. So because there are 3 ones, okay, you can see there are 3 ones. So that is why this is known as an odd function. Okay. Now, there can be also an even function. You can also have an even function. What is an example of an even function? Let us say we have some y2. Okay, y2 is what? You can have a, b, c bar, d bar, right? It could be a, b bar, c, d bar. It could also be a bar, b, c bar, d, right? And all. So if you will notice over here, how many bars are there? In this case, there are 2 bars. This case also there are 2 bars. This case also there are 2 bars. So that's why this is known as an even function. This is an example of an even function. Okay. Now, assume you have a third case. Third case. What do you have? You have A, B, C bar, D plus A, B, C bar, D bar. Will this be an odd function or an even function? What is this? Is this an odd function or an even function? What do you think? Because here, if you see the number of bars, this is 1 bar. Here you see the number of bars, there are 2. So that's why this is neither an odd or an even function. Okay. Right. So any queries still here? Anyone has any doubt? Anything you want me to touch upon or anything? You can let me know. Or else I'll
No, sir.
proceed further.
Understand.
Okay. Thank you. So now you have been studying about logic gates, etc. But how do you make it in a circuit? Okay. Acha, what is the condition for odd and even, sir? Okay, so how I am seeing it is, if you see this function, there is only 1 bar, right? Only 1 bar is there. Only 1 bar is there throughout. Here also 1 bar, here also 1 bar, here also 1 bar, here also 1 bar. So that means there are 3 highs. So for all the terms in that function, there are 3 ones. So that's why it is known as an odd function. In the second case, here what you see, this is 1, this is 1. So 2, this is 1, this is 1. So 2, this is 1, this is 1. So 2. So that is why it is known as an even function. But over here in the third case, there is a single bar here, but here there are two bars are there, right? So that's why one is an even part, another is an odd part. So it is not totally an odd function or it's not totally an even function. So that's why it is neither an odd function or an even function. Okay, so that's just the part of a function being odd or even. So now you have studied logic gates, etc. How do you make logic gates using a CMOS family? Okay, CMOS family. Okay, so let us say CMOS is basically you have one, this is a PMOS and this is a NMOS. So this is your PMOS, this is your NMOS, this is your drain, this is your source, this is the source of the switch, this is the drain of the switch, this is connected to your supply, this is connected to your ground, this is the gate, this is the gate, right? This is the gate of this, gate of this. They are connected in this case, okay? And this is the output. So this is your input A, and this will be your output A bar, okay? It is the complementary. So that's why this is CMOS. So this is your PMOS part, this is your NMOS part, okay? So the CMOS family has various advantages. That is, it's very easy to manufacture and its static power consumption is low, all right? And okay, what is your one doubt, you Sari?
Sir, case 3 is odd function, sir.
This Y3?
Yes, sir.
No, this is neither odd or not. It is not even odd, not even even.
Sir, A, B, C bar common and that D plus D bar is equal to 1 A, B, C bar.
Okay, that means you're saying we'll simplify, yeah?
Yes, sir.
Okay, ABC bar, D plus D bar becomes equal to ABC bar. But still, I'm not sure whether we can call it odd or even. I don't know. We can't exactly say. Hmm. Mm, we can't exactly say. Because if you see the even functions and all, you cannot simplify. Odd function also you cannot simplify. But here, if you are able to simplify, then I think I'm not sure. Okay, let us not consider this case. Let us consider a case where there's an odd function or an even function. Only those two cases. Okay. So now you have this CMOS family and you have logic gates. So you have a PMOS and you have a NMOS. PMOS means what? If you see this PMOS like this, okay. And these are like your gates. These are like your gates. So this is your PMOS. This is your NMOS. Okay. Yeah, P channel, N channel. So now if your input A is 0, okay, let us say input A is 0. Suppose your input A is 0, what happens to your PMOS? Your PMOS closes, but your NMOS remains open. Okay, that is your N channel MOSFET will act as an open circuit when your input is 0. But your PMOS circuit acts as a short circuit. It closes. That is, your switch gets closed. When your input is high, your PMOS, it becomes open, and your NMOS, it gets shorted. That means it gets connected. That is, the switch is closed. Okay, so this is the basic functionality of your PMOS, NMOS, and this forms your complementary metal oxide semiconductor family, the CMOS transistor, which is known as. Okay, so now we want to use this CMOS transistor and make a circuit, make a NAND gate or NOR gate or whatever. So this part of the circuit, this is known as an inverter, right? That is, if your A is 1, your output A bar is 0. If your A is 0, your output A bar is 1, right? So that's why this is known as an inverter. Now let us try a NAND gate or a NOR gate. So let us consider a combination, okay? This is your VDD, this is your ground, this is your output Y, this is your input A goes here, B comes here, B is also over here, okay? So this part of your circuit is known as your pull-up network. This part of your circuit is known as your pull-down network, okay? So let me just rub this off so that it's clear, okay? This is your A and B. This also is your A and B, okay? These are your PMOS. Now, what is your input to Y? Let us start with the pull down network. Okay, let us start with the pull down network. If your A is 1, okay, you just focus on the pull down network, on the PDA. If your A is 1, what will your output Y be? Okay, what will your output Y be? Will it be 1 or 0? If your A is 1, what is your output Y? 0, very good. If your
0.
B is 1, what is your output Y?
0.
Very good. If your Okay, so if your A is 1 or B is 1 or both are 1, your output Y is 0. And so this is similar to what is known as your NOR gate, right? A plus B OR. Okay, that is known as your NOR gate. Now, one condition we have not yet seen. What happens when your A is 0 and B is 0? If your A is 0 and B is 0 means what happens? Let us say this case, A is 0, B is 0 means this switch is open, this switch is open. But what is closed? This is closed, this is closed. So if your switch A is closed and your switch B, and let us say this one is closed and this one is closed, then your output Y becomes equal to 1. Okay. Right? Yeah. So that's why if you look through the pull-up network, if you look through the aspect of the pull-up network, your output Y will be what it is actually A bar and B bar. And if you look from the pull down network, your Y is equal to A plus B OR. Okay. Because if your switches are in parallel, then it becomes like your OR operation. If your switches are in series, it becomes known as your AND operation. Okay. So now you may ask that this is showing something else, this is showing something else. What is are they the same or are they different? Okay, I cannot hear you. Gracious. Okay, are they the same or are they different? So let us say you have Y equal to A plus B bar. That actually is equal to A bar and B bar. This is your De Morgan's theorem, right? Okay, let's try a different circuit to give better understanding. So if here, okay, this is your VDD, this is your A, this is your B. So A and B are in parallel on top, means A and B should be in series down. Okay, this is your A, this is your B. Right? This is your output Y. So again, this is your pull-up network. This is again your pull-down network. Right? Suppose A is 1 and B is 1. Then what will your output be? Y. What will your output be? Y. It will be 0, right? Okay, let us draw the truth table. It will be better. Suppose you have A, B, and Y. 0, 0, 0, 1, 1, 0, 1, 1. For 1, 1 case, the output Y is 0. What is the case when both A is 0 and B is 0? What will be the output? Y? Yeah, yes, Ram. That if the switches are in series, it represents AND function. Okay. So this represents A and B. And this represents A or B. No, but what you must realize is this is actually A bar or B bar. Okay, this is A bar or B bar. And pull-up network is fine. It directly becomes 1. But pull-down network, it goes to 0. Right? So if pull-down network is there, then your Y will be your PDN bar. And Y actually is equal to your PUN. So you can get the same function either by just analyzing the PDL or by analyzing the pull-up network. Okay. So not many of you are unmuting or answering. It would be better if you all could be more interactive so that I can know whether you're understanding or not understanding. Okay. It should kind of be sort of feedback
I'm
is
disconnected due to power cut. So
okay. No, that's fine. That's fine. Others also, I'd recommend others also can unmute and tell. Or you can send messages so that it can be more interactive, right? Yeah. So pull-up network, pull-down network, these are things which we have done. Now let us start with question. Okay. Okay, let us see some questions first. So what is the output of A XOR A bar XOR B? Okay. So the question is what? We have to do A XOR A bar XOR B. So what will this output be? So first let us start with A XOR A bar. What is A XOR A bar?
all ones.
Here A XOR A bar is 1.
A.
No, A XOR A bar is 1. Okay. Now 1 XOR B is what? 1 XOR B is B bar, right? 1 XOR B is B bar because it is inverted.
Yeah.
Yeah. So these are certain, this is certain things which you must recall. As you practice, you will get faster at this, so don't worry. You should, get comfortable using XOR, what is XNOR, and as you learn it, as you do it, tackle the sums, you will be able to do it. So it's not like, A XOR A bar is equal to 1. You may not need to by heart it, memorize it, and like if I tell you to get up in the middle of the night, it's not like you must be able to remember that. It is kind of logical and you can get that as well. Okay, so don't worry, but try to simplify. So suppose you have this question A XOR A bar XOR B. Don't start off by doing A bar XOR B. Start off by grouping the terms, right? A XOR A bar might be something. Then you analyze A XOR A bar. When you look at it, maybe after 2-3 weeks or that, you would have forgotten that A XOR A bar is equal to 1, right? But you can know that, you can write the truth table and you can get it. Or you can think and recollect and use some 1 or 2 inputs and you can get it that it is equal to 1, right? And 1 XOR B is equal to B bar. So a simple way to do it would be to use a truth table. You can have a truth table that is what XY, and the XOR of that is what 0 0 0 1 1 0 1 1. So what is that? 0 XOR 0 is 0. 0 XOR 1 is 1. 1 XOR 0 is 1. And 1 XOR 1 is 0. So if you are looking into the case where A XOR A bar you have to look. So this is your A XOR A bar, right? This is your condition A XOR A bar. This is 0 means this is 1. This is 1 means this is 0. So when you look at this condition of A XOR A bar, what do you see? You see a XOR output is 1, right? So you can apply that. In the next case, you're seeing that. So that is this case, right? So this is your this case. In the next case, you want to check 1 XOR B. So what you see, this is 1, right? And this is changing from 0, 1. What happens to your output? Your output is invert of that. That is 1, 0. That is why it is equal to B bar, right? So the truth table is able to, once you have the truth table, you can easily solve the sum. So knowing the truth table is important. And slowly these relations also, as you practice more and more, you will get very comfortable with them. Okay. So that's there. So let us consider this one. You have a 2-input XOR gate with inputs X and Y. The output of the XOR gate goes to an OR gate with the input X. What is the output of this circuit? Okay. So what is this question? You have an XOR gate here like this. This is your X and this is your Y. And this goes to an OR gate. Okay. X, Y, X. And this is your output. So what will this output be equal to? Let us say the output is F. Okay. So at over here, this is what? XOR Y. And your output F is equal to XOR Y plus X. That is OR of X. Now, how do you simplify it? You have X XOR Y, which you know. That is X Y bar plus X bar Y plus X. Right? So that what you can write it down as, you can take X common, that becomes equal to Y bar plus 1 plus X bar Y. Right? What does that become equal to?
X plus X bar Y.
X plus X bar Y. Yeah. Can this be further simplified?
No, sir.
No. Okay. Okay, so this is like how the circuit would look like. So you had this original circuit, but you can simplify it and make it a simpler circuit. So this is the way you should be comfortable with XOR gates. Okay. Let us go to next question. So what does a 2-input OR gate look like in a CMOS circuit? So you have to make an OR gate in a CMOS circuit. Okay. How do we do that? So OR gate is like a basic building block. You use OR gate many times. The easier way is you make an OR gate in a CMOS circuit using a NAND gate, using a NOR gate. We use a NOR gate. So NOR gate, how does the NOR gate look like? It will be like this, right? This is how it looks. No, it's the opposite. Mhm. Here, here, and let me draw the next page. Your A, this is your B, this is your A, this is your B, this is your supply VDD, this is your supply graph. Okay, so over here, what you will get A bar and B bar, or you can write it as A or B bar. Okay, that's the NOR gate operation. Then you connect it to an inverter. Okay, and this is your output. This is connected to ground. This is connected to VDD. This is your output Y. So what do you have? You have what? You have this A or B, the NOT of A or B. So this output Y becomes equal to A or B. So this part is your NOR gate. This part is your inverter. Okay. Any queries in this?
No.
Okay. Yeah. Okay, so if there are no queries, what we'll do is we'll take a break of 2 minutes and then we'll again start it. Okay. So just a small break of 2 minutes. So, okay, let's just check this question number 5. What happens when your minterms are 0, 3, 5, and 6? Okay. We have a question. Your minterms are what? 0, 3, 5, and 6. What sort of function is this? So what do you have? You have A, B, C. Then you have 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. You form the K-map. 0, 1, 2, 3, 4, 5, 6, 7. So what they're saying, you have for 3, for 0, for 5, and 6. So can you do any grouping in this one?
No.
Can you group any of these terms
No.
in the K-map?
No.
No.
Acha, wait. Sorry. Sorry, I was not using my headphones. Now is it properly audible?
No. Yes, we can hear you.
Okay. Thank you. Okay, so I think probably let me repeat what I said. So this is the K map, right? 0, 3, 5, 6. If you draw the K map, okay, this is 0, 1, 2, 3, 4, 5, 6, 7. So what do you have? You have it at 0, at 3, at 5, and at 6. So you cannot group any terms. You cannot do any grouping of the terms. So now because you cannot do any grouping of the terms, when such a K-map you get, you should try to correlate. It could either be a XOR gate or an XNOR gate. So now, is it a XOR gate or is it a XNOR gate? Okay, let us try to understand. So this is, let us say A, B, C. So this is what 0, this is what 0, 0, 0, 1, 1, 1, 1, 0, and this is 1. So what do you think? Is it a XOR gate or is it a XNOR gate? What do you think? So is it an odd function or is it an even function?
Neither. It's a odd function.
Odd function. Okay. What about others? Okay, someone is saying not odd, not even. Okay. Yeah, so let me clarify your doubt. So your minterms are 0, 3, 5, and 6. First of all, this is not like this is odd. This is not like these two are odd. These two are even. This is not the case. This is not like this is odd and this is
It's
even.
odd.
Yeah.
It's an odd.
No.
It's an odd.
Okay, no. It's an even function. It's an even function. So I've confused you guys. So let me just start. Let me just tell you why exactly it is even function. Okay. So summation of m has 0, 3, 5, and 6. 0 is what? It is 0, 0, 0. This is your 0. 3 is what? It is 0, 1, 1. This is your 3. What is 5? How do you represent it as? 5 is here 1, 0, 1. And 6 is what? 1, 1, 0. Right? So how many ones are there? How many ones are there? Can you tell me how many ones are there in all these cases? First case, how many one is there? How many ones are there? In this case, how many ones are there?
0.
Yeah, in this case, 0. And the next, it is 2, 2, 2. Okay. Yeah. So that's why there is an even number of ones. Okay. So that's why this is an even function. So if it is an even function, and in this case, that is all the terms, all these terms are coming, you know that this has to be represented using an XNOR gate. Okay, so that's why this will be represented by A XNOR B XNOR C. Okay. Okay. Yeah. So do you want me to repeat it or you have understood, or you want me to
We have
again
understood.
understood? Okay, okay. Thank you. Okay, so that's why this is an even function, and you should understand whether it is even or odd by counting the number of ones. Yeah. So next, what type of question is there? Sir also touched about regarding various arithmetic circuits. Sir discussed about adder, subtractor, and so on. Let us try. What is the circuit for A greater than B? Okay. What is it for A greater than B? So let us see, you have a number A and you have a number B. Number A has 2 digits. Okay. 2 digits means what? It has A1 and it has A2. B has 2 digits, that is, it has B1 and it has B2. Okay. So now, how can we check what condition is A is greater than B? So for that, what we have to do, and you should remember that they are unsigned. There's no sign bit, nothing. So you have A1, A2, B1, B2. So now you have to write a whole long truth table. Okay, how will we write the whole long truth table? That is 0, 0, 0, 0. This 0, 0, B is here for 4 terms. And this is 0, 1, 1, 0, 1, 1. Then what happens? This becomes 0, 1, 0, 1, 0, 1, 0, 1. And this has this whole 0, 0, 0, 1, 1, 0, 1, 1. Right? Then this is what again? 1, 0, 1, 0, 1, 0, 1, 0. And this becomes what? 0, 0, 0, 1, 1, 0, 1, 1. Then this is what? 1, 1, 1, 1, 1, 1, 1, 1. This is what? 0, 0, 0, 1, 1, 0, 1, 1. Okay, this is how you can draw the 64 or 4 bits truth table. Now, what is your minterm? Okay, what is your minterm number? This is what 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. This is your generic number. That is, you do binary to decimal, this is your number. Now, what is the value of A? Okay, when both is 0, 0 means what? This is actually 0, 0, 0, 0. The number is 0. If 0, 1 means what? It is 1, 1, 1, 1. 1, 0 means what? It is 2, 2, 2, 2. 1, 1 means it is 3, 3, 3, 3. What is the magnitude of B? In this case, it is 0, 1, 2, 3. Here again, it is 0, 1, 2, 3. Here again, it is 0, 1, 2, 3. Here again it is 0, 1, 2, 3, right? Now you have to find a condition when A is greater than B, right? So when is the condition when A is greater than B? Is it for this case? No, 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 no. Is it for 1 is greater than 0? Yes, right? That is 1 is greater than 0, yes. But for the next three cases, okay, let us try a better one. Let us try a better way. Let's try when A is greater than or equal to B. Okay, A should be greater than or equal to B. So in that case, what would be the change would be when A is 0, B is also 0, so it is equal to, so it becomes equal to 1. Next case, A is 0, B is 1, no, so that's why it is 0, 0, 0. Next case is A is 1, B is 0, 1, because A is greater than B. Next case, A is 1, B is 1, so A is equal to B, so that's why it is 1. Okay, the next case becomes 0, 0. Now again what? A is 2 is greater than B with 0, so that's why it is 1. A2 is greater than B1, so that's why it is 1. Then both are equal, it becomes 1. Then you have 0. Then A is 3 and B is 0, so it becomes 1, 1, 1, 1. Okay, any queries in this? How did we get this? Any doubts, any queries? So basically, we try to get the truth table of A greater than or equal to B.
So you only ask only A greater than B now.
No, I changed it. I changed it to A greater than or equal to B to make it more interesting. Okay. So good. So thank you. So now you can draw. Okay, once more, let me just go through. I have a question. I have a question. I want to find what is the circuit that will enable me to detect when A is greater than or equal to B. Many times we have the competition always, that I want to be better, or at least I want to be same with my friends, or I want to be better than my friends. Then I'm fine. I don't want to be less than them. Okay, let us assume that this is the question. That you are A and your friend is B. In terms of marks, in terms of stuff, many times we compare, right? So this is like that comparison. That is A, the number A, I'm comparing with the number B, and I want it to be true when A is either greater or equal to B. Okay, and A is a 2-digit number. B also is a 2-digit number, 2-bit number, right? So you have A1, A2 are the bits, B1, B2 are the bits. So we'll assume A1 is the MSB, A2 is the LSB. B1 is the MSB, B2 is the LSB. Okay. So then you write the A1, A2, B1, B2, the numbers, you write it down. Okay. The bits, you write it down. Then what is A1, 0, A2, 0? That is actually 0. That is actually 0. And so you get what is A in terms of the magnitude. It is 0, 1, 2, 3, you get. B also you get in terms of 0, 1, 2, 3, you get. Then you compare in which case A is greater than or equal to B. So here you have 1, 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 and again here you have 1s, right? So these are the various cases. So then we can find the K-map. We have to find the K-map. So we have to take what? 0, 4, 5, 8, 9, 10, 12, 13, 14, 15, right? This is the thing which we have to find. So let's go to the next page and draw. Right. So this is your A1, this is your A2, this is your B1, this is your B2. So then you have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, right? And this was 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. So what do we have? We have 0, we have 4, we have 5, we have 8, we have 9, we have 10, we have 12 is there, 13 is there, 14 is there, 15 is there. Okay. So now how do we solve this circuit? How do we minimize it? Any suggestions?
First, we have to group 4.
Okay. Which 4 should I group?
1, 1, 12, 13, 14, 15.
Okay, we can group this, right? We can group like this. Okay, then what can I do?
0, 4, 12, 8.
Then you can group this. Okay, you can group this. Okay,
5,
then what
13.
should we do? Yeah. Then we can group like this, right?
Yeah.
We can group like this also, or we could do like this also. We could group like this, right?
Yeah.
We can also group like this. Huh? And then you can group like that's left. Group like this. Okay, so let us start with this combination. This is what? It is equal to A1, A2. Then let us start with this combination that is equal to what? B1 bar, B2 bar. Then let us start with this combination. What is that equal to? Here A2 remains 1, 1. And here B1 remains 0, 0. So that is why it is equal to A1, B1 bar. And then let us go to this green combination. Here what remains? A1 is 1, A1 is 1 here. Okay, sorry. For this case, A2 is 1 and A2 is 1. And B1 is 0, B1 is 0. So it is what? A2 bar B1. Okay. And in this case, what it is? It is A1 is 1, 1. And B1 is 0 and B1 is 0. So it is what? A1 into B1 bar. No. Here also it is A2 bar, B1 bar, A1 into B1 bar. Okay. Which oct is satisfied? Which oct is satisfied? I can't see an oct. Can it satisfied here? Okay, someone. Okay. And then the last one, there is this one. This is what equal to? Here it is A1 is remaining the same, right? So this A1 and here you have B1 and you have B2 bar. Okay. So this is the combination. This is the circuit. Okay. Yeah, so this is how they've told you that this is your question. From that question, how do you get the answer? It's a little bit this is a little bit of a lengthy question. You should understand the reasoning and everything, and then you can solve it quickly. Okay.
Sorry, it's I think only A2, not A2 bar.
Where? Oh, yeah, sorry, it is A2. Yeah, it's A2. Thank you. So let me share. Here. I'm sharing the link for where you can access the YouTube videos and the drive link also. So the YouTube link is the link to the channel, and the drive link is where you can access the notes. Okay. Better understanding. So this session is being recorded, then it will be uploaded on YouTube, and then this notes also which I'm writing, I will make convert it into a PDF, and then I will upload it also, so you can access it later. Okay, so just don't mind the handwriting, that is the bad part, but just try to learn the content. So, what other question? So there's something known as a noise. Is noise good or bad? Can anyone say, is noise good or bad?
It's bad.
It's bad.
It's
Okay.
bad.
Yeah, it is bad. So if noise is bad, so what should we do? So noise can come in a circuit. Noise is there in a circuit and all. So then what should you do? Noise is something which you cannot escape. It will be there. So what to do in that case? So the earbuds which I am using, that is known as noise cancelling headphones. What it does is it has some mechanism by which the external noise, it sort of cancels out and all that, right? So in the circuit, we can design the circuit in such a way that we can reduce it. As Indu has told, we can design the circuit in such a way that what are the things which lead to noise, we can reduce that. Okay, but even if when we do all that also, still noise can come. Still noise can be present. So to overcome such a situation, we should have what is known as a noise margin. You should have what is known as a noise margin. So let us assume this is your circuit. This is your inverter. This is again your inverter, right? And this is your input circuit. So this is A. This becomes equal to your A bar. This again becomes equal to your A. So now, for one inverter, let us see. This end of the page. So V input, V output. Okay. So input signal, if it is between, let us say it is between 0 to 5. Okay. When your input signal is between 0 to 2 volt, you assume your input signal is 0. If your signal is between 3 volt to 5 volt, then your input signal is 1. And in this region, it is undefined. Okay, it is undefined. Yeah. Now, your output signal, again, it is between 0 to 5 volt, but your output could be between 0 to 1 volt and 4 volt to 5 volt. And this is sort of like your gray area, undefined. You don't know what exactly it is, right? So now, the output of this circuit is the input to this output, is the input for this circuit, right? So if your output of the signal is, let us say, between 4 volt to 5 volt, between this range, suppose your output becomes equal to 4 volt. and due to some noise, you have some noise, something is there, it goes down to 3.4 volt. Will it affect your output? Will it affect your next circuit or not affect it? What do you think?
It will affect.
It will affect. Okay. What about others? What do others think?
Sorry, say you said the input or the output?
No, there's a okay, let me just draw it better. Yeah, let me explain once again. Oh. So you have a circuit A. It is followed by an inverter that is leads to A bar. Then this is another circuit leads to A. Another inverter leads to A. Okay. Now A for one particular inverter, for any one particular inverter. So this is the input side, right? This is your input side. This is your output side. Okay. If your input is between 0, what numbers I took here? Yeah. If your input is between 0 to 2 volt, that means your circuit will detect that your input is 0. Okay. It will detect that your input signal is 0. If your signal is between 3 volt to 5 volt, it will detect that your input signal is 1. Okay. It will detect your input signal is 1. Now, this same logic gate at the output, what it will give, if your output is between 0 to 1 volt, it will give an output of 0. If your signal output is 0, the range will be between 0 to 1 volt. And if your signal output is 1, the range will be between 4 volt to 5 volt. Okay. This is your output of this inverter 1. Okay, this is your inverter 1. Now, let's put some space. This is your inverter 2, which ideally it should give you A, right? And 1 and 2 are similar inverters. So that is the input should be between 0 to 2 volt for it to be 0, or it should be between 3 volt to 5 volt for it to be equal to 1. Okay. So let us say your one case, let us go with one case at a time. Your input signal over here is 1 volt. That means it is actually 0 over here. So your output over here, A bar should be what? It should be 1, which means your signal will be between 4 volt to 5 volt. So let us say that your signal comes out to be 4.3 volt. Okay, it is 4.3 volt. So if I give 4.3 volt, assume there is no noise. Okay, so you assume there is 0 noise. So your signal over here comes again 4.3 volt. If I give 4.3 volt over here, this will detect it as 1, and then it will give an output of 0, which is again between 4 volt to 5 volt. So let us say it gives you again 4.3 volt. Assume, not 4.3 volt, sorry. It will give, let us say it gives you output 1 volt. It just gives you output 1 volt. Now, let's consider a case where there is noise. It gives you an output of 1 volt, which is 0. Here the output is actually 1, where this is 4.3 volt. But there is some noise. How much is the noise? Let us say the noise of minus 2 volt noise has come. Assume minus 2 volt of noise has come. I should have changed the color, sorry. Change the color. Assume your signal is 1 volt, which is 0. Here you get an output of 1, which remains at 4.3 volt. But by some misfortune, something, you have minus 2 volt of noise. Okay, minus 2 volt of noise. If you have this minus 2 volt of noise, this becomes equal to what? It becomes equal to 2.3 volt, right? So then this circuit doesn't know whether it is between 0 or 1. It comes in the range. This 2.3 volt, is it a 0 or 1? Can anyone say, is it 0 or 1? 2.3 volt.
It's undefined.
Yeah, it is undefined, right? So that will cause your circuit to malfunction. It will cause your circuit to malfunction. In which case your output is undefined. So that is what is known as the effect of noise. Okay. So now, how much noise can you tolerate? How much noise can you tolerate? Right? How much noise can you tolerate? So the worst case is, this is 4.3 volt is not your worst case. Your worst case will be when your output is 3 volt. When your output is 3 volt, and this input should be, no, sorry, your worst case is when your output is 4 volt, and this input can go as low as 3 volt. Okay, so that's why your noise margin for the high side will be 4 minus 3, that is 1 volt. So it can tolerate up to 1 volt of noise, it can tolerate. Okay. Similarly, if your output here is supposed to be 0, then worst case is when it is 1 volt over here, and this can detect up to 2 volt, right? It can detect up to 2 volt. So that's why your noise margin low. The noise margin low is equal to 2 minus 1, that is again equal to 1 volt. So 1 volt of noise it can tolerate. Okay. So these are certain simple questions which come with what is the noise margin, what is the, for the high, for detecting it to be high, noise margin low, etc. So you can understand how to do it and solve it. Okay. Yeah. So that's what we did. What is the noise margin we checked? There is now see what is parity. Does anyone have any idea what is parity?
Adding an extra bit.
Okay, you're adding an extra bit. And why should we add an extra bit?
Because of the perfect signal. If it is even, we do not have to add. If it is odd, we have to add one for perfect receiving signal or perfect.
Okay. So we were just discussing noise margin, right? That is how much of noise you can tolerate and everything. Now assume you have sent signal 110. This is the signal you have sent to your transmitter. At your receiver, what you should get? You should get 110. But assume you got 100. Assume you got 100, right? Then what do you know? How will you know whether you have received a correct output or not? So what they add is they add an extra bit known as parity bit. Parity bit. Okay. So what they do is they can add a bit called 0. You add a bit 0, you could add. So the receiver, you should ideally get 1100, but you got 1000. So what they know, we studied in odd function, even function. This is what? This is an even value. But this is also even. But in the receiver side, we got it to be odd. So then we know that there has been an error. Then we know that there has been an error. This means everything is fine. Let us take another output, another way. Assume this is 100. 100, then you have to add a parity bit. So should I add 1 or 0? Should I add 1 or 0?
1.
You should add 1 because you want the number of ones to be 1, so that you want even parity. Okay. So the receiver side, if I get 1 0 0 1, number of ones are even, then what do I say? It is correct, right? But if I got 1 1 0 1, then it is odd. Then we know it is not correct. Okay. Yeah. So this is the concept of parity. So what you have to do, you have at the transmitter side, you have to generate the parity bit. And at this side, you need to check the parity. So there are certain circuits for doing that. Okay. So the last thing which we'll look into today is known as hazards. So is hazard good or bad?
It's bad.
Yeah, it's bad. Yeah. So hazard is like something dangerous, right? So can a circuit be hazardous? Yeah, sometimes your phones could be hazardous and electronic gadgets, all the radiation, everything. There are certain standards where they try to limit the radiation and other stuff, but still there has some hazard. But the hazards which we are talking over here is not related to that. It is that there could be, what is known as a glitch. Okay, a glitch can happen. Glitch is something which it is like you have in some movie or in some screen or some part, something doesn't work as it should work. That is known as a glitch. So there is what is known as a type 0 hazard. Type 0 hazard means what? Your output should be 0, but suddenly due to a glitch, it goes 1 for a short period of time and then goes to 0. Then you have a type 1 hazard. Okay. Type 1 hazard is what? Your output should be 1 only, but suddenly it goes to 0 and goes to 1. Okay, this is known as a type 1 hazard. Then there is something known as a dynamic hazard. Dynamic hazard means what? It goes from zeros, it goes to 1, 0, 1, all this, right? I think I've written it opposite.
ये करो ना 12 बजे
So there are different type of hazards. So let me just check. I'll try to get the simulation up. Just hold on a minute. Okay, so are you able to see the screen?
Yes, we can.
Okay, okay. So if you look at this circuit, this is like generating your some signal. And then this is for you have a NAND gate. So can you tell what does this NAND gate do? Can anyone say what does it do? Both the input of the NAND gate is connected to the same signal, to A. A and A is coming. A and A bar of that. What is the output of the NAND gate? It will be A bar, right? You have a NAND gate. Like if a NAND gate, both the signals are the same, the output will be the bar. That's why this is A bar. Okay, this is A bar. Now, what is A and A bar? What is the output of A and A bar? What do you think is the output? A and A bar?
0.
0. Okay, very good. It will be 0. Now, we are like, you and me are human beings. Okay, I asked a question. It will be transmitted from my voice. It will go to my microphone. Then through Zoom, it will come to you. Then you will hear. So you will hear the question. Then you will take some time to process it. And then you will give the output. You will give the answer is 0. Right? Similarly, in your digital circuits also, there is something known as a delay. Okay, there is a delay. Between one signal to the next output, there is a delay. So because of these delays, we have these hazards or these glitches. Something which should not happen, it happens. Okay, so let us run the circuit and let us see what should be the result. Here, let us see. Okay. So this is my signal A. This is my signal A bar. This is my signal Y. Okay. My signal A is coming. It's going 1, 0, 1, 0, so on. A bar also is going 0, 1, 0, 1. It's the complement of it. Okay. And your output should be 0. It is 0 only. Suddenly it becomes 1. It should be 0 only. Suddenly it becomes 1. For a short duration. 0 and then suddenly it becomes 1. So why is that happening? Let us try to understand why is that happening. So let us zoom in over here. We will zoom in, right? We'll zoom in over here. What can you observe over here? Can you observe something? You observe over here. So let me start with this part. This is A is gone to 0. But my A bar, for it to go to 1, there is a delay. Okay, a delay of let us say around 10 nanoseconds or something is there. There is a delay. A has gone to 0. So A bar should become 1. But because of the delay in the circuit, 10 nanosecond delay, there's a delay from A to go from 0 to 1. Okay. But this does not impact your output Y. Your output Y is not affected. It is not affected for this case. But in the next case over here, okay, in this part, what has happened? A has gone from 0, it has gone to 1. Okay. And your output A bar from 1 to go to 0, it takes some time. Okay. From 1 to go to 0, it is taking some time. And then you can see there's a momentary high. So why does this momentary high come? It comes because at this point, okay, let us say from here, as well as in this part, A and A bar both were 1. And because of the delay in the circuit, this also becomes equal to 1 after that delay. Okay. So this is known as a static 1 hazard. There is suddenly there is from 0, it has gone to 1. Okay. No, sorry. This is static 0 hazard. That is the output should be 0, but there's occasional glitch of it going to 1. Okay. Any queries in this? No queries? Okay, very good. So you guys are very fast. So this is a software. This is known as Simetrix / Simplest Elements. So in the previous video which I uploaded, also I included the link where you can download this software. So this is a free software. Elements is like the preliminary basic version, which is free. The advanced version you have to pay it as a license and all that. It is complicated. So since many of us don't have access to that, I'm working on the Simetrix simplest elements for this course. So I just wanted to show some simulations such that you can appreciate these things. Okay. So this is done. Let us look for another one over here. Let us try static 1 as well. So this is the circuit for static 1 hazard. So static 1 hazard is what? This is A bar. And you're ORing it. So A or A bar, what is the output of A or A bar? What should be the output of A or A bar? Yes, someone just told something. A or A bar should be 1. Very good. Thank you. So now let us run this circuit. Okay, we'll run it. What you'll notice is here. So this is your A, this is your A bar. And your output Y is 1 almost all the time except at certain glitches. Okay. So why that is happening? It is similar. It is again the delay. That is your output A is 1. It is going to 0. And your output at A bar should go from 0 to 1, but there is a delay. So there is a portion of time when both A and A bar are 0. And after processing of the gate or gates delay also, that output suddenly goes to 0 for a short duration of time. Okay, so this is known as the static 1 hazard. That is, it should be 1, but occasional glitches when the input is going from 1 to 0 and certain situations, there is a glitch observed over here. Okay. So then let's try last one. So if you observe here, you have 4 A, B, C, D. Okay. So A, B, D, all of them are connected to VCC. That means all of them are connected to high. Okay. And you have the input C over here, which is going from 1, 0, 1, 0, and so on. And this is a complex set of circuit. Okay. This is a complex circuit, right? You have AND gates, you have an OR gate, you have a NAND gate, you have an AND gate. Okay. So because A, B, D are 1 and only C is changing from 0 to 1, ideally the output Y should have only certain combinations. Okay. But let us see what is happening. Or let us now better try to analyze the circuit first and then try to see. So let us say, take this circuit example. How is this circuit? Check it. Okay, by the way, this is all optional. So if someone wants to leave, they can leave. This I just wanted to show so that if people want to understand, visualize, they can understand. For those whose time is up, who are tired, who are exhausted, who are hungry, you can leave. Rest. If you're interested, you can see this. Okay. Yeah. So now let us look at this circuit. What I have over here, I have, first of all, A is equal to 1, B is equal to 1, and D is equal to 1. Okay. So only my C is going from 0, 1, 0, 1. Only C is changing. Okay. So now in my circuit diagram, what I have A and C. That is what? You have A and C. Good. Now what else do I have in my circuit? I have C, NAND, and D. So C is connected to a NAND gate. Okay. This is D. C is connected to an AND gate. And then that is again connected to an AND gate here, where this is connected over here and B is connected over here, right? And this entire thing is connected to another OR gate. Whoa. They are connected to an OR gate. Okay. And then the output of the OR gate is connected to an AND gate. This is connected to another AND gate. Okay. And this is also connected over here. Okay. It's very complicated. But you guys are smart, so you should be able to do. So your A is 1 and this is your C. So 1 and C, what will be the output of 1 and C? What will be the output over here? 1 and C is what?
C.
Yeah, that is C. Very good. Now C and D and the not of that. So D is also what? 1. So what will this be?
C bar.
So this will be equal to C bar. Very good. So then what will this be over here? Over
C
here,
bar.
what will it be? B is 1 and this. So here also it will be C bar, right? So C or C bar, what should be the output over here?
1.
It should be 1. Okay. And here it is equal to C bar, right? So 1 and C bar, what should be the output of 1 and C bar?
0.
Why? 1 and C bar, no? Any signal, any AND gate, 1 and A is what? A. So 1 and C bar also should be equal to C bar only, right?
Yeah, C bar.
Yeah. It means, yeah, it means C bar, right? Good. So now let us check in the circuit whether that is happening or not. Okay. So you have your C, then all these are connected to 1. Let us simulate it and check. Okay. C. So your Cn is going from 1, 0. Let me not check this, change the simulation time. It's 200 nanoseconds. Let me just increase it. Simulator transient need 250. So this is your C. It is going from 1, 0, 1. So what should your output be? Your output should be 0, 1, and 0. But instead, there are multiple transitions. There are multiple transitions in between. So this is known as your dynamic hazard. Okay, this is known as your dynamic hazard. You should go from 0 to 1 and then again go back to 0. But in between, there is a certain transition. And that is because of the delays in the gate, right? See, from Cn to Y1, there's a delay. Okay. Then from Y1 to Y2 to Y3, there's a delay, right? All these delays, they contribute to your output changing abruptly, not abruptly, changing in such a fashion. So this is known as a dynamic hazard. Okay. So this is a simple example. there'll be more, like when you guys start working or making projects, you will find more and more difficult, more and more complicated examples. So don't get scared. You'll have to tackle much more difficult things as well. But you can, slowly increase the complexity. Okay, see how I started. I showed you static zero hazard. Then I showed you static one hazard. Then I showed you dynamic hazard. So you can slowly start building the circuit. What when you try to learn something, try to learn a new software, don't say I will make, full ladder circuit or one which has, carry in, carry out, all those things. Don't suddenly start all. You start with a simple circuit. You study the simple circuit, you run the simulation, you understand how the software works. Then you can make a slightly complicated circuit. That also works. Then you make a little more complicated circuit. Okay. So that's the way, like when you have these circuits and everything, you can, simulate it on the software. You can see how it looks like, what it happens, and all. So this is just for you to get some interest in doing these simulations. So I hope they're interesting for you guys. And I hope you guys also will download the software and practice it so that you can learn better. Because you can see that there are many things Sir has taught, right? Sir has taught so many things. He has taught, these are like, the delays and the glitches and all these things, right? Sir has also taught, what he has taught, these things are there. He has taught half adder, he has taught full adder, two adders, ripple carry adder. All these things, if you want to understand more or if you want to use it in your projects, it would be good if you can make these circuits and test it and check it. Is it working or not? Right? So that you can know whether you have made a connection mistake or something. Okay. So
So
any other queries?
sorry, this tool is free.
Yeah. This version of this tool is free. Simetrix/simplest elements. This is free.
We can download it in from Chrome.
Yeah. You can download it from Chrome, but this software will only work on Windows PCs. Okay,
Okay.
that is a limitation. Yeah. Hmm. So in the previous video which I uploaded, I had put the link to downloading Simetrix as simplest elements. So you can check in that video. In this video also, which I'll be uploading, I'll be putting the link so that you can easily access. And those who are interested, those who want to learn more, you can download the software as well. Okay.
Okay, sir. Thank you.
Yeah. Okay. What about others? Any others have any queries, any suggestions, any things you want me to tackle for the next week? How do you want me to proceed? Let me know. Because feedback is very important, necessary for me, because many of you or some of you will be giving that test, the exam, and in the assignments also, like you'll have to solve it and you'll have to do. So how would you want me to tackle the next session? Like, should I focus more on the theory or should I focus more on the sums or should I focus on the simulations? What do you want? Because at the end of the day, these sessions are designed for you. Okay, these sessions are for you. Whatever doubts you have, whether problems you have to ask it to me, right? You can ask me. I may not be able to tell you the answer. I'll try next time and all that. Okay, sequential circuits is coming the next further part of the course, right? So that's why I cannot start it now. When sequential circuits are being taught, then I can do that. Oh, yeah. Yeah, sequential circuits add, a lot of more interest and everything. It is a little bit more complicated than combinational circuits, but yeah, it's interesting and practically required as well. Okay, so if there are no other queries, I'll end the session. So thank you for joining. Thank you for participating and thank you for patiently listening to me. So I hope these sessions are useful to you and I'll be uploading this video on YouTube and also these notes on the drive. So all the best for your preparation and everything. Thank you for joining.